Welcome, nocturnal minds aboard. Your learning journey starts now. So, picking up from our last discussion on functional concepts and scientific idealization, we naturally arrive at a fundamental aspect of how science operates: measurement. Is the bedrock, right? You can't really do science without measuring things. But here's the kicker: try defining exactly what measurement is. Philosophers often say it's about assigning numbers correctly to physical variables. Sounds simple, but then comes the headache: what does correctly even mean? And how do we know if we've done it right? That's where the real fun begins. For anyone actually doing the measuring, the burning question is straightforward: did I do it right? But philosophers, being the troublemakers they are, layer on another dimension. Does this measurement actually measure what we think it measures? Think about something controversial, like an IQ test. Does it truly capture intelligence? Or is it just a cleverly disguised reflection of test-taking skills, cultural background, or whatever else correlates with those scores? This brings us to two main camps. On one side, you have the nominalists, who basically say, forget about some objective reality. The measurement method itself defines the concept. If you measure it this way, that's the concept. On the other side, the realists argue that measurements are tools to uncover objective quantities out there in the world, independent of how we choose to measure them. It's a big philosophical divide. Let's dive into the nominalist camp, starting with the heavy hitter operationalism, championed by Percy Bridgman. His core idea was radical ditch the whole realism debate. He famously declared that a concept is nothing more than a set of operations. So, if you define length by using a specific type of ruler in a specific way under specific conditions, then that's your definition of length for that context. It means any measurement operation is automatically correct for its own concept. It's a tautology. Now, Bridgman later admitted this sounded too rigid, so he shifted focus. He argued that analyzing scientific practice through operations is incredibly useful. It helps reveal hidden assumptions and differences in how people actually work. For instance, consider length. We measure it differently depending on the scale, lining up rulers for everyday objects, complex physics calculations for atoms, or timing light for stars. Operationalism suggests we have as many distinct concepts of length as we have distinct measurement methods. Mind-bending, but it highlights the practical focus. Now, within nominalism, there's a slightly less extreme view: conventionalism. Thinkers like Harry Poincaré pushed this. They agree that measurement methods define usage, but they draw a line between mean how we use a word in all sorts of ways, and definition a rule we agree upon to regulate that usage. Conventionalism says we get to choose the correct measurement method by agreement. Since nature doesn't hand us down the perfect way to measure time, we make a convention. Poincaré put it beautifully when discussing time. Time should be so defined that the equations of mechanics may be as simple as possible. He concluded, there is not one way of measuring time more true than another. That which is generally adopted is only more convenient. See? Convention rules, not some absolute truth etched in space-time. It's about practicality and agreement. Why did these nominalist ideas gain traction? A big reason is the sheer number of things scientists study that are fundamentally unobservable. We can't see atoms directly, or dark matter, or even the exact distribution of energy in a quantum state. And then came Einstein's bombshell dropping on the physics community. He showed that the seemingly obvious notion of distant simultaneity, saying two events happened at the same time, even if far apart, was actually impossible to determine absolutely. It always relies on some arbitrary choice of measurement procedure, none of which are inherently more true than others. This shook the foundations. Bridgman, influenced by this, saw operational analysis as a way to sidestep such deep philosophical quagmires. His goal was essentially to say, let's just focus on the operations we can perform and agree upon, and avoid needing some unborn Einstein to tell us we're wrong about the basics. Okay, enough with the nominalists. Let's flip the coin and look at realism. Realists fundamentally disagree. Measurement methods don't define the concept. They are tools to discover an objective reality. There's a real quantity out there, and we're trying to pin down its value. So, the question, is this measurement method or the correct one for concept C? Is absolutely crucial. If you're an empiricist wanting to test theories involving C, you need to believe you can measure C correctly. Sadly, naive realism is rampant. Everyone assumes their familiar thermometer measures temperature correctly, or their scale measures weight accurately. But reality is often messier. Take a mercury thermometer. The common picture assumes uniform expansion between freezing and boiling points. But how do we know mercury expands uniformly? We'd need to compare it to real temperature values. But how do we get those without trusting another thermometer? We're stuck in a loop. This leads us to what Heizuk Chang calls the problem of nomic measurement. Imagine you want to measure quantity X, but it's hard to observe directly. So you use another quantity that's easier to measure, relying on an empirical law connecting them. X equals f of y, fine. But how do you check if your function f is correct? You need data points of x and y. But to get the x values, you need to calculate them using f in the first place. It's a chicken and egg problem. You could try a different method to measure x, but then you just kick the can down the road. How is that new method justified? Or maybe derived from a grander theory? Well, that theory itself needs empirical support, which almost certainly involves measuring x or other quantities tied to it. It's a tangled web. This specific headache is just a sharp example of the broader issue. Our observations are always theory-laden. Our instruments, our interpretation, they all come loaded with theoretical baggage. And this theory-ladenness isn't just a minor nuisance, it's extreme in modern science. Think about measuring temperatures near absolute zero, properties of quarks, or distances to galaxies. These rely on incredibly complex theoretical frameworks. Pierre Duhem pointed this out ages ago. Justifying your measuring instruments inevitably pulls you into the whole network of scientific beliefs. Defending realism requires a strategy for dealing with this interconnectedness, this holism. One potential escape route, hinted at earlier, is a milder form of operationalism. If we can define concepts based on well-defined, stable operational procedures, think basic laws like Archimedes' principle for levers or Snell's law for refraction, which seem remarkably robust across various situations, maybe we can anchor our empirical data securely, keeping theories separate and allowing them to evolve. Herbert Fagel noted that these middle-level regularities often provide a stable enough foundation. Whether you're a realist or a nominalist, practitioners are obsessed with precision. But hold on, precision isn't accuracy. Precision refers to how specific or consistent a measurement is. If you measure the same thing multiple times and get very close results each time, you have high precision. Accuracy, however, is a realist concept. It's about whether those results are close to the true value. You can be super precise, but wildly inaccurate. Think of a clock that's always 5 minutes slow. It's precise, but not accurate. Sometimes statisticians use terms like validity accuracy and reliability precision, or talk about error versus uncertainty. The key takeaway is precision is necessary for accuracy, but it doesn't guarantee it. Interestingly, sometimes the same techniques help achieve both goals. Let's zoom into the physical sciences. We take for granted that everything measurable is numerical. But history shows otherwise. Think about velocity. Aristotle considered it a quality, hard to quantify. Heat was another Aristotelian quality transformed into measurable temperature and heat quantity. Even now, quantification can change what we mean. Acidity became pH based on hydrogen ion concentration, a much narrower, more specific concept than the old qualitative idea. Color mapping perception onto wavelength is even more drastic. But quantification doesn't always work out. Chemical affinity attempts to assign numbers to how strongly substances react failed because the underlying ordinal rankings were shaky. Color perception studies also showed that psychological closeness between hues doesn't neatly map onto the linear spectrum of wavelengths. Numbers aren't magic wands. Despite these hurdles, the drive towards precision has been immense in the physical sciences. Why? Because better precision often leads to better science and technology. Astronomy kicked things off centuries ago with meticulous observations by folks like Tycho Brahe. Then came incredibly precise balances, enabling Cavendish and Lavoisier's work on conservation of mass, proving heat wasn't a substance. John Harrison's marine chronometers revolutionized navigation by improving timekeeping precision. Surveying techniques got so good, they helped settle debates about Earth's shape and provided the basis for the meter. Coulomb and Cavendish developed torsion balances for exquisite force measurements. Micrometers allowed for precise engineering. Over the 19th century, this obsession with precision spread throughout experimental physics and eventually into many other lab-based sciences. It became a culture. But here's the philosophical wrinkle. How do you iteratively improve precision? Let's use temperature again. Suppose all you have are thermometers accurate to E degrees Celsius. How do you judge a new thermometer that claims to read to 0.1 degrees? You need to compare it to something you trust. But you only trust your E-degree thermometers. So, you're using a less precise instrument to validate a more precise one. Relying on theory doesn't solve it either. Remember the nomic measurement problem. At every step of improving precision, you face this choice. Which competing higher precision standard do you adopt, given the current lower precision standard? Chang argues this choice isn't trivial. It's a deep philosophical and practical issue with no easy realist answer. It involves judgment, convention, and sometimes just picking the one that works best for your current purposes. Once we accept some nominalism, the power of convention really comes into play. Remember the solar time versus clock time debate? Clock time, declaring the sun's movement irregular, seemed absurd to astronomers who revered celestial regularity. But by convention, we adopted clock time. Any concept like time has layers of meaning. Precise measurement inevitably narrows or changes some of those layers. Bergson famously argued that quantifying time completely misses its subjective lived experience. We've seen endless debates over units, Fahrenheit versus Celsius, metric versus imperial. Custom is powerful. The French Revolution tried decimal clocks and 10-day weeks alongside the metric system, and they flopped. Unit choices aren't arbitrary, they reflect deep assumptions. Light years assume constant light speed. Kelvin temperature arose from thermodynamics, aiming for universality beyond specific materials. Even the original Celsius scale was upside down. These choices shape how we understand and measure the world. Now, let's shift gears to the social sciences. Max Weber famously warned that measurement here is fraught with unique difficulties, arguably worse than in physics. Why? First, unlike physics, where we can tweak concepts like acceleration to fit neat laws, social science concepts often deal with messy human behavior that might not follow strict laws or be perfectly measurable. Second, it's a double task. You need both a theoretical definition of your concept like economic freedom and a practical way to measure it in the real world. Third, measuring things like psychological states is always indirect. Fourth, creating measures usable across different cultures or populations often means sacrificing nuance for comparability. Fifth, just observing or measuring social phenomena can change the phenomenon itself. Sixth, ethical and political norms heavily constrain what we can measure. And finally, we often want to measure vague aggregates like GDP or household labor, raising tricky questions about what counts and how. So, how do social scientists tackle this? Measurement theory offers a framework. First, you need a mathematical representation of your concept, fitting it into your theoretical model. For example, trying to define economic freedom mathematically, perhaps as the number of available options. Potanek and Su did this formally, setting out axioms for what economic freedom should look like and proving their definition met those criteria. Second, you need a representation theorem to show your definition actually captures the intended properties. But theory is only half the battle. Third, you need empirical procedures to connect the abstract concept to the real world. How do you measure someone's actual economic choice set? Psychometrics often blurs these steps, maybe using questionnaires and statistical tests to argue they measure depression. A huge part of social science methodology is constantly refining these measurement tools. A major headache in the social sciences is that measures often aren't neutral. They embody values or purposes. Take the Human Development Index, HDI. It includes life expectancy, education, and GDP. Should political freedom be included? That's a value judgment about what constitutes human flourishing. Even seemingly technical decisions can have value implications. Consider revising the Consumer Price Index CPI to account for cheaper outlet stores. Sounds fair, right? But as Julian Rice pointed out, it could disadvantage groups like the elderly or rural poor who can't easily access outlets. A common response is to let users decide the values. But this leads to chaos, proliferation of measures, difficulty comparing them, and immense challenges in execution. Think about defining poverty. Is it absolute or relative? Relative to median income, mean income, or something else? Count households or individuals. How do you weight them? These choices drastically affect results and impact, requiring expertise far beyond typical users. Alright, let's pivot to a different but related theme, mechanisms. While the word's been around since the 16th century, philosophers have recently embraced it as a central concept. The mechanist view argues that understanding the world requires identifying mechanisms, systems of interacting parts, producing behavior, or processes unfolding through time. Think photosynthesis, or a car engine. This approach challenges the older logical empiricist tradition, which put laws of nature front and center. Mechanists argue that focusing on mechanisms better reflects actual scientific practice, especially in biology and social sciences, but even in physics. The idea isn't new. Descartes and Boyle used it, seeing everything reducible to interacting particles. But contemporary mechanists drop the metaphysical baggage while keeping the explanatory strategy, explain phenomena by uncovering the underlying mechanisms. So, what exactly is a mechanism? Two influential definitions highlight key features. Machimer, Darden, and Craver MDC say mechanisms are entities and activities organized to produce regular changes between start and finish conditions. Glennon defines them as complex systems producing behavior via interacting parts, governed by direct, invariant generalizations. What do they share? First, mechanisms are productive. They do something, they produce an outcome or behavior. Second, they consist of structured parts, not just a random collection, but entities organized spatially, temporally, and functionally. Third, they exhibit regular behavior, though not necessarily exceptionless. Think synapses firing reliably, but sometimes failing. Fourth, they are hierarchical. Parts of a mechanism can themselves be mechanisms, leading to nested levels of explanation, from molecules to cells to organisms to ecosystems. Now, don't confuse this with Wesley Salmon's earlier work on causal processes. Salmon also talked about mechanisms in his 1984 book, focusing on causal processes like a moving baseball and causal interactions like the bat hitting the ball. Both involve interacting entities, explaining events through continuous processes. But Salmon's focus was different. His interactions didn't need to be regular like the parts in a mechanism, and he wasn't emphasizing systems or the hierarchical structure as much. Salmon was primarily interested in explaining single events, whereas the contemporary mechanism movement often aims for general accounts of repeatable processes. Salmon's work was foundational, but the recent surge in mechanism studies has taken a slightly different, more system-oriented path. How do scientists find and represent these mechanisms? MDC suggests they start with a mechanism sketch identifying the overall behavior and growth structure, like Watson and Crick's central dogma sketching DNA to RNA to protein. Then, they fill in the black boxes, localizing functions and figuring out the details. This involves strategies like looking at parts bottom-up or reasoning from function to structure top-down, sometimes using clever tricks like perturbing the system to see how it breaks. Importantly, mechanists argue models represent mechanisms through similarity, not perfect isomorphism. Models aren't true or false in the same way theories are. They're useful representations to varying degrees. We choose models based on pragmatic needs. Also, models are abstractions. They simplify reality. We study exemplars like squid neurons to understand synaptic transmission, but success with the exemplar doesn't automatically guarantee the model applies elsewhere. Mechanisms and causation are deeply intertwined. Mechanisms cause events, but can we define causation purely in terms of mechanisms? Glennon argues yes, largely. He suggests that causally related events are linked by intervening mechanisms. Turning the key causes the car to start because there's a mechanism involving the ignition system between those events. But wait, isn't interaction itself causal? Glennon tries to break the circle by appealing to hierarchy. The interaction between parts is itself a mechanism, whose parts interact in a lower-level mechanism, and so on. However, this hits a snag at the bottom. Fundamental interactions, like electrons repelling each other, might be causal, but lack a deeper mechanistic explanation. So, a complete causal theory might still need something else, perhaps counterfactuals. Salmon offered a different process-based account of causation. Another debate concerns MDC's emphasis on activities as a distinct ontological category beyond just entities and interactions. Whether this is necessary remains contested. Proponents argue the mechanism paradigm better captures modern science, citing its prevalence in journals. It's particularly dominant in biology and neuroscience. Why? Because these fields often deal with regularities that aren't exceptionless laws, and many generalizations like Mendel's laws or the central dogma are themselves explained by describing the underlying mechanisms. But does the mechanism approach have limits? Some worry about complex biological systems with many interacting parts or emergent properties where the whole behaves unpredictably from the parts. Can we still apply the mechanistic framework? Similar issues arise in social sciences. Does physics, the traditional paradigm science, fit? Some fundamental interactions seem non-mechanical. Yet, physics uses aggregate models, planetary orbits, gas behavior that could arguably be viewed mechanistically. Philosophers like Nancy Cartwright argue even physics benefits from mechanistic explanations, suggesting the paradigm might be broader than initially thought. So, wrapping up, we've journeyed from the tricky business of measurement, grappling with philosophical debates about realism versus nominalism, the practical demands of precision, and the unique challenges in social contexts. We then shifted to mechanisms, exploring how this framework offers a compelling alternative to law-based explanations, emphasizing productive systems and processes, and providing tools for understanding complex phenomena across diverse scientific domains. Though it too faces questions about its ultimate scope and how it connects to causation. Both topics highlight the intricate ways we attempt to understand and quantify the world around us.